Hi there and welcome back to the College Physics series. In today's lesson, we're going to be talking about vector operations such as addition, subtraction, and scalar multiplication. Be sure to download the guided notes in the description so that way you can follow along with me as I perform the examples. Thank you for being here and let's get started. Imagine you're steering a boat across a river. You want to head directly north, but the current is pushing the boat to the east. So forward, north, we have the velocity of the boat. And towards the east, we have the velocity of the river. Even though this boat is aiming north, the boat is actually going to be moving diagonally because of the water's influence. So the actual direction of motion for this boat will be something more like this, pointing in that direction. How can we describe this motion in both directions at once? This is where vectors come in. Vectors help us describe movement when both direction and magnitude matter. In today's video, we'll explore how vectors work, why they're useful, and how we can combine them to analyze more complex movements, like our boat crossing the river. Let's start by reviewing two important types of quantities, scalars and vectors. Scalars are quantities that only have a magnitude or size. For example, if you say you walked 5 meters, that's a scalar because it only tells us how far you walked, not where. Vectors, on the other hand, give us both a magnitude and a direction. So, if you say you walked 5 meters north, that's a vector because now we know both how far and in which direction you have traveled. We can represent vectors using arrows, where the length of the arrow shows the magnitude and the direction of the arrow shows, well, the direction. Let's quickly talk about how we draw vectors. You're going to first begin a vector with a dot, like this. That is the starting point for any vector, and we call this a tail. Then you're going to draw a straight line wherever you need this vector to point. Let's say it's there. At the end, I'm going to draw what we call the tip, or you can call it a head, because it represents, or it looks like the end of an arrowhead. Tip or head. You can call it either name. So to give this vector a name, to make it special, we need to give it a special symbol. Let's say this represents a displacement. In order for me to indicate that this is a vector, I need to add a vector symbol on top. If I just want to indicate the magnitude, the size of this vector, I can write it with just the same symbol, but without the arrowhead. So with an arrowhead indicates that it's a vector, and without the arrowhead indicates that you're describing the magnitude of this vector. For the rest of these notes, I'm going to be utilizing a lot of examples concerning displacement. However, all of the rules that I'm going to be applying to these displacement vectors can be applied to any vector that you are going to learn in the rest of your physics career. Let's take a closer look at how we represent vectors, starting with displacement vectors. Let's imagine we walk 6 meters to the east. We can represent that movement with a vector that points east and is 6 meters long. So I'm going to choose this as my starting point, and I'm going to draw out the length of the vector to be 6 units. After I've crossed 6 units, I'm going to place my arrowhead, and here's how I'm going to name my vector. I'm going to name it D with an arrowhead to represent this as a vector, and it's going to be equal to a set of parentheses with a comma. The reason why I set it up this way is because one entry is going to indicate the magnitude, the other entry is going to indicate the direction. So my magnitude is 6 meters east. So the left blank spot would represent the magnitude, and the right spot would indicate the direction. And that is how you write vectors. Now, let's say we have a friend that lives in a house, and this friend is going to go get the mail outside from the mailbox. Your friend starts from this point and follows this path to get to the mail. The neighbor is also going to be getting the mail with an exact same setup. This will be person A and person B. We are going to label them vector A and vector B. The question is, are these two vectors equal? The answer is yes. Even though they started at different places, their vectors are equal because they both move the same distance in the same direction. Vectors are equal if they have the same magnitude and direction, regardless of where they start. Now let's talk about how we combine vectors. This is called vector addition. Imagine you walk 4 meters east, then 3 meters north. What is your net displacement? Let's draw this out. So here I have my first vector. I'm going to label it vector A, and that is equal to 4 meters east. Then what happens is that I travel 3 meters to the north, and I'm going to call this vector B. These are two separate motions, which is why I've drawn them like this. Now the question is, how do I add these together? To find the total, or the net displacement, we need to draw a new vector from where you started to where you ended up. In order to find the net displacement, I'm going to draw my initial vector, my first one, and that is 1, 2, 3, 4 to the east. Then immediately at this spot, I'm going to begin my second vector. And the next one was 3 meters to the north. The sum of these two vectors is the vector that begins at the very beginning and points in the direction of the head of the last vector. This blue line is what we call the resultant. And we can call this vector C. The red was vector A, the second one was vector B, where the resultant vector is equal to the sum of A plus B. Here's another question. Does the order matter in which I add these vectors? Because I first wrote vector A and then I drew vector B. Let's switch it up and see what happens. So instead of first drawing vector A, I'm going to draw vector B and go 3 meters to the north. Then I'm going to start vector A right where vector B ended, and I'm going to go 4 meters to the east. My resultant will always be from the very beginning, my first initial spot, and points in the direction of the very end, to the head of the last vector that I added. If I notice, these two vectors overlap themselves identically, meaning I get the exact same answer whether you go east first and then north, or north first and then east, your total displacement is the same. This is the commutative property of vector addition. Now that we understand vector addition, let's look at two ways to add vectors graphically: the tip-to-tail method and the parallelogram method. The tip-to-tail method is simple. You place the tail of the second vector at the tip of the first vector. For example, if you walk 5 meters to the south, so I'm going to draw my first vector 5 down. This is going to be vector A. And then we're going to have another motion of 8 meters west. And this will be vector B. For you to understand the tip-to-tail method, I'm going to label the tips and the tails so that way you can see the order in which we add. So in order to add these two vectors using the tip-to-tail method, I'm going to take vector A, and then I'm going to place the tail of vector B at the tip of vector A. So the tips and tails are going to belong together. The resultant starts from the tail of the first vector and points in the direction of the tip of the second vector. And that would represent the resultant, A plus B, which we can call vector C, or you can call it any other vector. Another way to add vectors is the parallelogram method. I'm going to draw out the same vectors. If I want to add using the parallelogram method, I'm going to place the vectors tail to tail. So I'm going to grab my first vector, I'm going to place it down, and then I'm going to place the tail of my second vector, and I'm going to match the tails together. My next step is to complete the parallelogram. How I do that is that I'm essentially going to take vector A and I'm going to copy it. I'm going to make a copy right here. I'm going to take vector A and I'm going to slide it over until I get to the tip of vector B. And I'm going to perform the same thing for vector B. I'm going to copy it, and then I'm going to slide it down until I complete the parallelogram. In this case, I've constructed a rectangle. Remember, a rectangle is a parallelogram. My resultant vector is going to be the diagonal of this parallelogram. It's going to begin at the tails and point in the direction of the tips. And this is the resultant, A plus B, which we can also call C. If you notice, if I overlay these two diagrams, I'm going to get the exact same resultant vector. What happens if we multiply a vector by a number? That is what we call scalar multiplication. Let's say, for example, I have a car that drives 6 meters east. I'm going to represent that vector, I'm going to establish the tail, and draw 6 units to the east. And I'm going to call this vector A. If we multiply this vector by 2, I'm going to build a new vector that we call 2A. When we multiply a vector by a scalar, which just means a number, you are going to affect the magnitude. If A was 6 meters to the east, then 2A will be 12 meters to the east. Therefore, vector 2A is going to be twice as long, and that would be vector 2A. Finally, if the car doesn't move at all, we have what is called the zero vector. The zero vector is a vector with no magnitude or direction. We represent the zero vector with just a dot. It has no shape, size, or direction, and we can give it the special symbol 0 with a vector symbol on top. That is what we call the zero vector. You can also get the zero vector if you add two vectors together such that they equal to 0, meaning they cancel each other out. Let's see what happens if we multiply vectors by negative numbers. Let's say I walk 5 meters east. I draw my tail, and I'm going to draw the length of this vector to be 5 meters to the east. I'm going to call this vector x. If I multiply this vector by -1, I'm going to be finding negative x. To get negative x, I'm going to flip my vector to point it in the opposite direction, and that would be negative x. So multiplying by a scalar affects the magnitude, but multiplying by negatives affects the direction. So x was 5 meters to the east. Negative x will be the same 5 meters, but to the west. We have altered the direction of these vectors. So what if we want to subtract vectors? For example, if one person walks 7 meters north and another walks 5 meters south from the same point, how do we find the difference? Here's the starting point. One vector is going to go 7 meters to the north. I'm going to call this vector A, and that is going to be 7 meters north. Then I'm going to have another person start from the same point, and they are going to walk 5 meters south. I'm going to call this vector B, which is 5 meters south. In order for me to subtract these vectors, we can think of it as adding the opposite. This is how I would write vector subtraction. But how I'm actually going to perform vector subtraction is through vector addition along with scalar multiplication. So I can rewrite this as A plus negative B. Here's a simpler way to think about this. If I do 10 minus 5, that's the same thing as if I take 10 and I add negative 5 instead. I get the exact same answer. So let's see how we do this. First, I need to draw vector A. So I'm going to draw vector A here. But I'm not adding vector B to it. I'm adding minus B. So remember what happens when we multiply by a negative. The vector flips. This one went from east to west. So if vector B is 5 meters south, then minus B is going to be 5 meters pointing towards the north. So from the same starting point, vector negative B is going to be 5 to the north. 1, 2, 3, 4, and 5. And this is what I'm adding. Using my vector addition rules, the tail of the second vector goes on the tip. So in total, my resultant is just from the very beginning to the very end. And that is a total of, it is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So the quantity A minus B is going to be equal to 12 meters to the north. And that is the resultant that you can give any other name, C. Let's now apply what we've learned to a conceptual example. Suppose we have two vectors, A, which is 3 meters east, and vector B, which is 4 meters to the west. We want to find 2A minus B. Let's draw both of these vectors out. A would be 3 units to the right, and B is going to be 4 meters towards the west. The first part I'm going to realize is that vector subtraction can be rewritten as vector addition. So what I'm really going to add together is 2A, and I'm going to add negative B to that. So I need to find what 2A is. If A is 3 meters to the east, 2A is going to be 6 meters to the east. To find minus b, all I have to do is flip the direction, reverse it. So b is 4 meters towards the west, minus b would be 4 meters towards the east. So to add these two vectors together, I'm going to draw the first one, vector 2a, and then I'm going to add vector negative b to it. Remember, the tails and tips line up. The resultant vector starts from the very beginning, from the first tail to the last tip. So the total will be 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. The space I'm including here for the arrowhead does not matter. That doesn't actually count. So the quantity, or the vector 2a plus negative b is equal to 10 meters to the east. Well, this is 2a and that's minus b. Now it's your turn to try. Here's a similar example, but this time the vectors are at angles. And that is going to wrap up our lesson on vector operations. Today we learned how vectors help us describe motion with both magnitude and direction. We explored how to add, subtract, and apply scalar multiplication to vectors. If you found this lesson helpful, please consider liking the video, subscribing to the channel, and sharing it with others who might benefit from it. And don't forget to leave your answers to the practice problem in the comments. I'd love to see how you did. Thank you for watching and being a part of the College Physics series. I look forward to seeing you in the next lesson.